Hello. Hello. Hey, Rayshana.
Hey, Nisha. Hi.
All right. Waiting for everybody else to get here.
Hold on.
There you go. Eden. Nico. All right. We're all here.
Good morning.
Morning. All right.
Belser's here.
Mm-hmm. I see y'all.
Kelly's here.
I see everybody.
All right.
Good. All right. Got that taken care of. Okay. So today we're going to talk about two things. We're going to talk about proteins, and we're also going to talk about cardiovascular disease. Okay. So proteins are the last macronutrient in your diet, and they're made up of units that are called amino acids. And they get that name because the nitrogen group on one end is called an amino group. And then on the other end of the building block, there's a carboxylic acid group. And so amino acid describes basically the backbone of the building block. And then there's an R group that comes off of the middle carbon that can be any of a collection of several different um, atoms, and you can see them here. These are all the amino acids. And again, they fall into three groups based on the properties of the R group. They can either be charged, which means that the R group has an electrical charge at neutral pH. They can be polar, which means that they're going to contain electronegative atoms in their R group and are more likely to associate with charged or polar groups, while the charged groups are more likely to associate with polar or charged groups of the opposite charge, because opposite charges attract each other. And then there's nonpolar amino acids that don't have very many electronegative atoms in their R groups, and as a result, they tend to cluster with each other, and that's usually on the inside of the molecule in the interior. Okay. Um, Basically, when an amino acid is used to build a protein, what happens is that they get connected to each other through a process called peptide bond formation. And that's the dehydration synthesis reaction that happens in a place in the cell that's called the rough endoplasmic reticulum, or sometimes it can happen in the cell in an area that's called the cytoplasm. Okay. The rough endoplasmic reticulum is just a series of membranous sacs that are kind of connected to each other, sort of like a maze. And there are particles called ribosomes, which are the protein building factories that make the proteins that the cell needs in order to function. And they get that information to build those proteins from a molecule called a messenger RNA. And that comes out of the nucleus of the cell. And the process of building those proteins is called translation. Okay? So one amino acid at a time, following the instructions in the messenger RNA, we generate what's called the primary structure of the amino acid, which is the amino acid sequence. Now, in the boxes here are the essential amino acids, and those are the ones that you can only get by eating them in your diet. The other amino acids, your body has the ability to create from other sources. So they're called non-essential, okay? But basically, when you eat protein, the reason that you eat protein is to make more protein, right? So you eat protein like in your meat, and then you tear that down, and then the amino acids that come out are then going to eventually be absorbed by the cells in the tissues of your body and are going to be used to make the new proteins that make you a functioning organism. Okay, so it's a breakdown and reassembly process pretty much. Okay, so this is a look at how the proteins are built.
Proteins are polymers of amino acid monomers. Every amino acid contains a central carbon atom bound to 1. An amino group, 2. A carboxylic acid group, 3. A hydrogen atom, and 4. A group that differs from one amino acid to another and is represented by the letter R. This dehydration synthesis reaction has created a protein consisting of 4 amino acid monomers.
So that process happens at the ribosome, and it happens because the cells in the tissues of your body need a particular protein made that's going to do a particular job for it, okay? If you wanted to describe what proteins do for living things, they basically participate in all life processes, okay? So you could think of them as the tools of life. They do things like speed up chemical reactions and defend against disease and tell the cell about what's going on outside the cell. And they also help to give the cell structure, okay? So there's a lot of different roles for these proteins, and the reason they can do so many different jobs is because you can assemble those amino acids in any order and any length and build almost any tool, okay? So the tools that result from this come out of the primary structure, okay? Once you built that chain, what's going to happen is that that chain is going to start to fold up on itself automatically, obeying again that second law of thermodynamics, which says that if you consider a system, it tries to get itself in the low energy state, the easy state, okay? So this is a look at the different levels of protein structure.
Each protein has a unique primary structure, a particular number and sequence of amino acids making up the polypeptide chain. 20 different amino acids are used to build proteins. Theoretically, the various amino acids could be linked in almost any sequence, forming an almost infinite variety of different proteins. This illustration shows some of the amino acids making up the primary structure of a protein. The structure of a single generalized amino acid is shown below. The main backbone of every amino acid is the same. This is what forms the backbone of the polypeptide chain. It is the R group, which projects out from the backbone, that makes each of the 20 kinds of amino acids unique. Different amino acids have different properties that affect the folding of a protein. Thus, primary structure ultimately determines the shape of a protein, which determines its function. In most proteins, parts of the polypeptide chain are coiled or folded, forming twists and corrugations. This is secondary structure. The turns and folds of secondary structure contribute to the protein's overall shape. One kind of secondary structure is the alpha helix, where the chain twists. Another is the pleated sheet, where the chain folds back on itself, or where two regions of the chain lie parallel to one another.
Secondary structure results from hydrogen bonding between atoms along the polypeptide backbone. Oxygen and nitrogen atoms along the backbone exert a strong pull on electrons, giving them partial negative charges, and leaving nearby hydrogen atoms with partial positive charges. These negatively and positively charged atoms are attracted to one another at regular intervals along the chain, causing parts of the protein to twist or fold back upon itself.
Superimposed on primary and secondary structure is tertiary structure, irregular loops and folds that give the protein its overall three-dimensional shape. The irregular folding of tertiary structure results from interactions among the R groups of amino acids. Acidic and basic R groups ionize, and these positively and negatively charged groups may form ionic bonds. Polar forces also contribute to tertiary structure. Hydrophilic or polar R groups may hydrogen bond with one another or turn outward and hydrogen bond with the surrounding water. Hydrophobic, nonpolar R groups cluster on the inside of the protein away from water. Tertiary structure may be further stabilized by strong covalent bonds between sulfur atoms in certain R groups. Some proteins consist of two or more polypeptide chains. The fourth level of protein structure, quaternary structure, results from the combination of two or more polypeptide subunits. Quaternary structure is stabilized by the same sorts of attractions that stabilize tertiary structure. Hemoglobin, the red oxygen-carrying protein of blood, is an example of a protein with quaternary structure. It consists of two kinds of polypeptide chains. Two of each, a total of 4 chains, make up each hemoglobin molecule.
So the types of jobs that proteins can do in the human body include structural proteins. A lot of those are fibrous. They're strand-like, they're water-insoluble, and they're pretty stable. They're tough. Most have tertiary and quaternary structure, and they resist stretching and twisting. And examples of those kinds of proteins include keratin, elastin, and collagen, and contractile fibers in muscle like actin and myosin. To give you an example, keratin and collagen make up a lot of what hair and nails are, okay? Collagen is also a big part of your skeletal system, okay? Collagen and elastin are a big part of your skin, which is pretty tough stuff, protecting you from the outside world, okay? In order for all these proteins to do their job properly, they have to be in their normal shape. And that only happens when the protein is in the environment that allows that to occur, okay, which is basically body temperature and body pH. If your body suffers from a disease state, if things go wonky, okay, then we could shift the pH or we could shift the temperature, and the result is that we could create conditions in which the proteins begin to lose their normal shape, and that's called denaturing. And if the denaturing happens and the protein can't work anymore, and then the life processes in the cells in our tissues are going to stop, and then you're going to die. Okay? So that's why the body works real hard to try to maintain conditions compatible with life, and that's a process called homeostasis. Your body uses your nervous system and your endocrine system to control your other body systems to make sure that things like your blood pressure, your blood sugar, your body temperature, the pH of your blood all stay within a range that keeps you alive. Okay? Sometimes when you get diseases, what happens is that you go outside that range and you get sick. Then if you go way outside that range, you're going to die. Okay? And the reason for that, in part, is because of the proteins losing their ability to do their job. Globular proteins are shaped kind of like particles, okay? They're spherical, they're water soluble, they're very sensitive to changes in the environment. They have tertiary and they have quaternary structure, and they have areas on their surface where important chemical events happen, and we call those active sites. Examples of globular proteins include antibodies, which are proteins that protect us against disease by attacking invaders, attaching to them, and tagging them for destruction. There's hormones, which are chemical signals that are sent in the blood that travel to other tissues and then tell those tissues to perform a certain task. And then there's chaperones. Those are proteins that help other proteins fold up. And then finally, enzymes, which are proteins that help to speed up chemical reactions so that they happen fast enough that we're able to produce things that the cells and the tissues need quick enough for them to survive. If we didn't have enzymes, those chemical reactions would happen so slowly that the cell would die, okay? So that's denaturation, right? Globular proteins, any protein really, can denature if we mess around with the temperature and the pH and the salt concentration that the protein is in, because most proteins are going to be in a liquid environment. And it can be reversible if you restore normal conditions, but sometimes it's irreversible. If you've ever fried an egg, you've seen an example of irreversible denaturation. The clear part of the egg when you crack it is mostly a protein that's called albumin, and it's meant to provide nutrition for the growing chick. But when it hits the hot frying pan, that heat causes the albumin to lose its normal shape, and it forms a semi-solid. And there's no way to make that go back to the way it was before. Okay? So that's an example of a denaturation event. You've changed the function of the protein, you've rendered it inactive because you've ruined its shape. It's kind of like if you had a toolbox and somebody went in and bent all your tools, right? Then you wouldn't be able to do anything with them. They wouldn't work properly. Chaperones are globular proteins that help other proteins get into their normal shape. So they sort of help tertiary and quaternary structure happen, okay? They also help proteins move across membranes, and they can help the breakdown of damaged proteins or denatured proteins, basically proteins that have been ruined and that the cell can't use anymore. Stress proteins are molecular chaperones that respond to extreme conditions like low oxygen situations or shifts in pH, and they help the cell survive during stress that it can deal with. And they can also delay the cell aging by helping repair damaged proteins and folding them back up. One of the things that happens when chaperones get messed up is that the cell can die because they have such a big role in helping other proteins get to where they need. There's a disease that you've probably heard of called mad cow disease, okay? And it comes from eating meat that contains a chaperone that has been messed up, okay, has folded improperly. And it's so small that when you eat that meat, the chaperone protein can cross across your digestive system into your blood, and then from there into your central nervous system, where your brain and your brainstem and your spinal cord are, and it'll turn the whole thing into gelatin in just a few days, and you'll die. So where does mad cow come from? And the answer is it comes from poor farming practice. Um, one of the ways that you can make more meat more quickly to get to market is that you can add to the feed of chickens and cows bone meal, which is ground up bone. It has a lot of protein in it, but it also contains nerve tissue. And in that nerve tissue are these messed up chaperones. What happens when the animal eats it is that the chaperone can get in there, can get into the animal's bloodstream, and get into the animal's nervous system, and then destroy all of that tissue and create new chaperones that are messed up in the process. And those messed up chaperones are called prions. Okay. And then if you eat that meat and don't know it, and it has that prion in it, then you can end up with mad cow. Okay. So we don't have that problem here in the United States because we have farming practices regulated by the federal government that states that all beef and chicken is 100% USDA grain fed. That's what it says on all your beef at Kroger's, and usually says so somewhere on the chicken label. Okay. Any case of mad cow that's happened in the US has been found to come from meat that was received from outside the United States, from places like South America or the UK or any of the other places where they don't have lots of grain production, and so they have to use this way of improving the protein content of their feed so that they can compete. Okay, so if you stick with U.S. beef and U.S. chicken, you're going to be okay. All right. This disease was actually first described in New Guinea, where this wasting phenomenon over a few days that the people would lose function and then die was found to be common, to be endemic among the New Guinea tribesmen. And they thought maybe it was a genetic disorder or maybe it was a pathogen, but it didn't seem to follow any of those modes of transmission when they looked at the data that was associated with the condition, which was called kuru. But what they finally were able to ascribe it to was the practice of the New Guinea tribesmen in honoring their dead. When the head of the household would die, they would eat him because they were cannibals. And the result of that is that they would eat nervous tissue, which contains prion, and they would end up in many cases with the disease. Okay. We have a similar condition here in the tri-state called mad deer. Okay. Mad deer comes from a few things. Number one, we kind of limited hunting. As a result, the deer population has exploded, and you can see deer on city streets, walking down suburban avenues, and even here in Cincinnati in the city. You might remember a story from a couple of years ago of a deer walking through the plate glass window of a jeweler in downtown Cincinnati. Okay. You'll see these stories of deer doing strange things, and some of that behavior is thought to be the result of the fact that the deer have now snuck out of the woods and are eating your gardens and your garbage. And in that garden and garbage material, it can be some nervous material and can be some prion, and the result is they can end up with mad deer. Okay. So you have to be careful about things like venison, right? You want to make sure that it didn't come from a deer that was similarly affected. Otherwise, you could end up with the disease as well. Okay. So that's an example of a disease that comes not from a living pathogen, but a non-living pathogen. Okay, enzymes. What are enzymes? Well, these are just proteins that help chemical reactions happen more quickly, okay? And they do that by lowering the activation energy. Now you might say, well, what does that mean? Well, normally in a chemical reaction, for something to happen, two molecules or two elements have to bump into each other with enough force that you can break and then make some new chemical bonds, okay? And that process, if it happens just in a test tube or in a flask, relies on just random collisions. So you can speed the chemical reaction up by doing things like warming the reaction or by increasing the concentration of the things that are reacting, okay? But if you do that in a living system, what'll happen is that you'll create conditions that'll kill the cells in your tissues. So the enzyme is a tool that lets that chemical reaction happen without having to do all of those things. And the way it works is that it actually grabs the molecules that are going to react and forces them together in a way that they'll produce the product that the cell needs, and then it lets go of the product, and then it repeats the process, okay? So what happens as a result is that you make a lot of what the cell needs real fast, and the cell can continue to do its work. It can continue to live. There's millions of enzymes, and they're all specific for different reactions, okay? They are all proteins, and the information for building those enzymes all comes from messenger RNA, okay? So let's look at what catalysts do, which is what an enzyme is.
For any reaction to occur, even one that releases energy, some energy must be added to get the reaction going. This energy is needed to break bonds in the reactant molecules. The energy needed to start a chemical reaction is called the energy of activation, EA. This required energy input represents a barrier that prevents even energy-releasing reactions from occurring without some added energy. How does a living cell overcome the energy? A special kind of protein called an enzyme is the answer. An enzyme serves as a biological catalyst, increasing the rate of a reaction without being changed into a different molecule. An enzyme does not add energy to a reaction. Instead, it speeds up a reaction by lowering the energy barrier. An enzyme is very selective. Its three-dimensional shape allows it to act only on specific molecules, referred to as the enzyme's substrates. As the substrates bind to the enzyme's active site, they are held in a position that facilitates the reaction. This takes less activation energy than the unaided reaction. Products form and are released. The enzyme emerges unchanged from the reaction. Because of the specific fit between enzyme and substrate, each enzyme can catalyze only one kind of reaction involving specific substrates. Thousands of different enzymes may be required to carry out all of a cell's metabolic processes.
So just like a key only goes into a particular lock, an enzyme is only going to latch on to particular molecules to help those chemical reactions happen, okay? Now the advantage of this, using an enzyme, is that the enzyme not only is specific, but in many cases it can also be regulated, meaning it has an on and off switch and it has a volume control, okay? Functional enzymes called holoenzymes can be made up of two parts. There's the apoenzyme, which is just the protein part of the enzyme. And then sometimes you'll have a cofactor and or a coenzyme. Cofactors are just metal ions, and you get those in your minerals in your diet. And a coenzyme is a vitamin, okay? And you also get those from your diet. They're naturally occurring in both your plant and your animal sources, okay? The enzyme is always going to be specific for a particular substrate, and they're always named so that they end in ASE, and then the prefix describes the reaction that they do, Like a hydrolase uses water to split a chemical bond, and an oxidase oxidizes a particular molecule. Okay, you can see here just a diagram, kind of what you saw before. The active site on the surface is where the substrates are going to go and fit in, right? And then the magic in that active site is that we can make and break chemical bonds really easily, and then we can let go of the product, and then the enzyme can circle back and do the whole thing again. Okay, now I told you guys earlier that they're regulated in many cases, right? Sometimes what will happen is that you'll make enough of the product that the cell is happy with the amount that you've produced, and you don't need that enzyme to keep doing this anymore. And so what will occur is that the buildup of this product will turn around and bind to another location on the enzyme and slow it down, okay, until the concentration of this product drops again, and then it'll let go of that other site, and then the enzyme will crank back up, okay? So it's basically a way to control the speed at which the enzyme does its work, okay? So it's like a volume control, or in some cases, it can click the enzyme off completely until you get below a certain concentration of the product. And that's important because that helps the cell avoid wasting resources and time, okay? So kind of cool. Different proteins in your diet, right? Complete protein is coming from animal sources, like animal sources or soy, which contains sufficient amounts of the essential amino acids. Incomplete protein comes from plant sources that contain all 9 essential amino acids, but one or more of them is not adequate for protein synthesis, so you have to mix and match, okay? Complementary proteins are food sources that are incomplete proteins by themselves, but when you combine them with another source, then you get complete protein, okay? An example would be grains and legumes, okay? Grains would be things like rice or corn or wheat, okay? And legumes would be things like beans and peas. And if you eat one or the other just exclusively on their own, you won't have complete protein. But if you put them together, you will, okay? So an example would be red beans and rice, right? That would be complete protein. Proteins perform a lot of functions, right? They're important in tissue building and maintenance. They are important in nitrogen balance. They help to control our energy storage and support our metabolism because they're the enzymes that do the work, okay? They aid in our nitrogen balance, and our nutrient transport. They support immune function. They're important because they basically do all the processes that we associate with maintaining life. They support tissue growth. The quality of the dietary protein needs to be assessed in the diet, right? If you're a vegan or a vegetarian, you need to make sure that you get complete protein in your diet by mixing and matching, okay? And we usually add protein to the diet when you're sick in order to compensate for the repair processes that are going on while you're recovering from your illness, which include things like building new tissue, okay? The recommended daily allowance of protein is 0.8 grams per kilogram body weight for healthy adults. Protein's acceptable macronutrient distribution range, its AMDR, is between 10 to 35% of your total calories. Underconsumption can lead to protein energy malnutrition. Examples include things like kwashiorkor and marasmus, which we'll see a picture of here in a minute. And that usually comes from lack of protein or lack of complete protein in the diet. Vegan diets can also lack B12 because it doesn't naturally occur in plants, so you need to take it as a supplement. And protein is kind of at the bottom of the energy per gram of in your diet, right? Calories per gram, 4 calories per gram for protein, which is less than carbohydrates, and that is less than fats. Okay, so a good way to lose weight is, again, to have a diet that's high in protein and high in fiber. Okay, this is kwashiorkor. Okay, you see this a lot in third world countries because the diets often lack protein content. Okay, um, the the ability to do raise farm animals and stuff is limited in a lot of these countries because of the environmental conditions. And so frequently with a low protein diet, what will happen is that you'll see this situation with muscle wasting and this distended belly, right? Now, why is this occurring? Well, the muscle wasting is because there's so little protein in the diet that the body is going to your own protein to try and keep you alive, okay, at the expense of your muscle mass, okay? The distended belly here is the result of a condition in the blood in which you're not making enough albumin. Your liver, which is a big organ on the right side of your abdominal pelvic cavity, just underneath your diaphragm, has as one of its jobs to make albumin for the blood. And the purpose of the albumin is to help the blood hold on to its fluid volume. So when the liver doesn't have the building blocks to do that, you don't make enough albumin and you lose fluid to other body compartments. And that's what's happening here. There's a large membrane called the peritoneum that lines the abdominal pelvic cavity, and the blood vessels in the peritoneum are losing fluid volume to the abdominal pelvic cavity, and that's what results in this swelling. Okay, so the way to fix this is to put protein back in the diet. Okay, and we can do that through protein supplements. We can do that by providing meat. Okay, and we can do that, if we're careful, with plant sources as well. Okay, you'll also see this condition in individuals that have liver damage. You generally see hepatomegaly in kwashiorkor and marasmus. That's an enlarged liver because the liver's working real hard to try and make protein that it can't make, so it swells up. And people that drink too much or that use a lot of recreational drugs, one of the other jobs of the liver is to take those drugs and that alcohol and turn them into something that can be cleared from the blood by the kidneys so that you can pee it out. Well, if you overwork the liver by abusing these things, then what happens is you start to damage the liver tissue to the point where it can't do its other jobs. And you'll start to see an enlarged liver and scar tissue on the liver. And you'll also see other liver functions start to suffer. And you'll see this sort of distended belly with the fluid in it. Okay, that's a hallmark of people that are in the late stages of something called cirrhosis of the liver, which is usually a result of abuse of alcohol. Okay, all right. With that, let's take a break. Let's come back at 11:20. Okay, and we'll talk about cardiovascular disease. So let's put that up here. There we go. I'll see you guys back at 11:20. There are dogs. Every boy. Okay, we're back.
Yeah.
Everybody here?
I'm here.
All right. So next topic is cardiovascular disease and dietary adjustments we need to make for people that are suffering from cardiovascular disease. So one of the things that we notice in the Western diet, like in Western Europe and the United States, is that we have usually a diet that's very high in calories and very low in satiety, meaning it's real easy to eat a lot of calories and not feel full. And the result of that is an epidemic of obesity, which produces conditions that put you at risk for coronary heart disease. All right. The way this works is that when you eat more calories than you burn, the excess calories get stored by your liver as fat, and that accumulates in your body. And the blood vessels in your body, as a result, get longer. And when that happens, the heart, which is your blood pump, has to pump against more resistance. And that causes it to enlarge, and that puts an extra strain on the heart. And it can get to the point where the heart has to work against so much force that it literally can't pump the blood anymore. It can't squeeze hard enough to shove the blood out of the heart through the rest of the body. And that's called congestive heart failure. Okay. Another thing that can happen as a result of putting on excess weight is that the cholesterol and the triglycerides in your blood can rise really high, and then they can collect as plaque on your arteries, including the arteries that supply blood to the heart. And the result of that is that your blood pressure goes way up, and then in many cases you can block a blood vessel that feeds a particular organ or tissue. Okay, that happens in the heart. You can block the arteries that feed the heart, and that can cause portions of the heart tissue to die, and that results in a myocardial infarction or a heart attack. Okay, the job of the circulatory system is to supply blood to the tissues, and in the blood is contained nutrients and oxygen. Okay, and the hormones that promote cell signaling and communication. All right, and also it helps to regulate our body pH and our body temperature. Okay, we need the oxygen to make enough energy out of the fuel we take in out of the blood to keep our cells and tissues alive. All right, and so that is why the heart and the lungs work together to deliver oxygen to all the tissues. So it's critical that the heart continuously pump. To maintain heart healthy conditions, we have to cut down on the cholesterol and triglycerides in our diet, and we have to have an exercise program that burns enough of those calories so that we don't gain a lot of weight. Okay? An example of a risk factor here, hypercholesteremia, promotes atherosclerosis, right? The deposits of plaque in the arteries causes their lumens, which is the opening in the middle of the tube, right, to get tiny. And when you try to force the same amount of fluid through a tinier hole, you increase the pressure. And that's bad because that can put strain on little tiny blood vessels called capillaries, and that can make them burst. And if that happens, then everything that's supplied by those capillaries will die because the blood supply has been cut off. The other problem with having these plaques deposited in the arteries is that the slow flow of blood through those tiny openings makes it more likely that the blood will clot. And then those clots can travel to the heart or to the lungs or to the brain. And the result in the brain would be a stroke. The result in the heart would be a heart attack. And the result in the lungs would be a pulmonary embolism. Okay? All of those will damage tissue. High density lipoproteins are the good cholesterol, and what they do is move the cholesterol from the blood to the liver to be cleared. All right, so if your HDL levels are high, that means you're sort of in scrubbing mode. All right, So levels greater than or equal to 60 milligram per deciliter provide protection against heart disease. So we like those levels to be at that level or higher. LDLs are bad because they do the reverse. They transport cholesterol out of the liver to other locations, and if they're high, what happens is you're going to tend to deposit those plaques on those arteries. Okay, so levels less than 130 milligram per deciliter is what we shoot for. All right, this can promote hypertension, right, which is a blood pressure greater than or equal to 140 over 90 under the age of 60, and greater than or equal to 150 over 90 over the age of 60. Okay, so your blood pressure gets checked routinely when you go to the doctor's office, and that could be an indication of underlying disease. Essential hypertension, while they say here no clear cause, basically it's lifestyle choices, right? It's your diet and your exercise regimen and how much weight you put on. That's the cause of essential hypertension. Secondary hypertension can be a response to a medication or to a particular disease. Okay, for instance, people that have kidney disease have trouble with hypertension. Certain medications can promote hypertension. All right, and for that, we absolutely know what the problem is, and we know how to make the adjustments. Okay, things that you can modify in order to improve your cardiovascular fitness include your LDL and HDL levels, the amount of saturated fat in your diet, your lifestyle, and your use of alcohol and tobacco. Okay, diabetes mellitus is often an outcome of obesity because when you eat a lot and you don't do a lot of exercise, your insulin levels stay really high. And when your insulin levels are high all the time, eventually the tissues in your body start to ignore your insulin signal, and that leaves the sugar behind in your blood, and that high sugar is the manifestation of type 2 diabetes. Okay, so you can overcome type 2 diabetes with diet and exercise. It can be done. A waist circumference of greater than 40 inches in men or greater than 35 in women is going to put you at risk. Things that you can't change: your age, your gender, your family history. Risk factors include older age, if you're male, and if you have a family history of coronary heart disease. Okay. One example of a condition that you can't modify is familial hypercholesteremia. And what happens in this disease is you inherit a defective receptor for these LDL and VLDL particles that are in the blood, right? The receptor is basically the gripper on the cell surface that pulls the lipoprotein in and lets you use what it's carrying. Okay, well, if you don't have the proper number of grippers, or if you have a bad gripper, then what's going to happen is that cholesterol and triglyceride level in your blood is going to rise. Okay, and so there are different versions of this disease. There is full-blown hypercholesteremia where you don't have any effective lipoprotein receptors, and you get that because you get two bad genes, one from your mom and one from your dad. Okay, and the other is mild disease where you get one bad gene. Okay, and then normal would be two good genes. Okay, so that's an example of something that there's no way you can change. You can use drugs to try to manage it. Okay, but you're not going to change your genetics. Right. Cardiovascular disease include coronary heart disease, where you get blockage in the coronary arteries, which actually supply blood to the heart muscle itself. And heart muscle, once it dies, doesn't come back and is replaced by scar tissue. And so after that, the heart is permanently weakened. Okay. Then there's heart failure, where the heart's not able to maintain adequate circulation. And that could be the result of things like congestive heart failure, where you build up so much resistance in the circulatory system that the heart literally can't pump anymore. And then there's myocardial infarction, where you have so little oxygen supplied to the heart muscle that you kill it, okay? So that's a heart attack, all right? So how do we deal with this? What dietary changes can we make? You want a low-fat, low-cholesterol diet, okay? There's a website here that talks about therapeutic lifestyle changes. You might want to take a look at that. High fiber, high protein, high exercise, no tobacco, no alcohol, okay? Daily intake of cholesterol, less than 200 milligrams. Saturated fat, less than 7%. Trim fat, remove skin from things like chicken and fish. Broil, bake, and grill instead of fry. Use spices and low-fat dairy products. Use plant-based oils. Increase your fish intake, because those are the good fats, the ones that have the unsaturated fatty acids in them, including things like tuna and salmon, right? And then get support from your friends and your family, okay? Cardiovascular disease is often the outcome of something called metabolic syndrome. And what are the highlights of metabolic syndrome? Abdominal obesity, right? Greater than 40 inches in men, greater than 35 in women. Triglycerides greater or equal to 150 milligram per deciliter. Low HDL, men less than or equal to 40, women less than or equal to 50. High blood pressure, and essentially a high cholesterol level and a high triglyceride level in the bloodstream, okay? So let's take a look at hypertension.
Hello, in this video, we're going to talk about hypertension or high blood pressure. This is an overview and introduction. Hypertension is defined as blood pressure of 140 over 90 millimeters mercury or greater. The main goal of treatment is to decrease the risk of mortality and of cardiovascular and renal morbidity. The signs and symptoms of hypertension include headache, dyspnea, high blood pressure, possible retinopathy and visual changes, chest pain, and sensory or motor problems. There can also be signs of end organ damage due to hypertension if the hypertension is untreated and severe. We will talk about end organ damage towards the end of the video. So what is blood pressure? Well, it is the product of cardiac output and the total peripheral vascular resistance. So here is a heart pumping blood out. This is the cardiac output. And together with the total peripheral resistance, makes up the average blood pressure. Risk factors for hypertension are obesity, high alcohol intake, metabolic syndrome, diabetes, high sodium intake, sleep apnea, dyslipidemia, old age, and family history. Hypertension can be a disease in itself, or it can be secondary to another condition, an underlying disease. Let us look at the differential diagnoses. Hypertension can be categorized as primary, also known as essential hypertension, or secondary hypertension, which is hypertension as a result of an underlying, often reversible cause. Primary hypertension is basically genetics and lifestyle. Secondary causes of hypertension include coarctation of the aorta, pheochromocytoma, hyperaldosteronism, Cushing's syndrome, renal artery stenosis, chronic kidney disease, polycystic kidney disease, nephritic and nephrotic syndrome, obstructive uropathy, hyperthyroidism, and hyperparathyroidism. There's also sleep apnea, chronic alcohol use, use of oral contraceptives, non-steroidal anti-inflammatory drugs, illicit drugs such as cocaine or methamphetamine, and preeclampsia in females. So those, again, were some causes of secondary hypertension. The pathological vascular changes that occur in hypertension occur slowly. Normal vessels have good blood flow. However, in hypertension, and as hypertension progresses, there is vascular changes, remodeling, and hypertrophy. In the early stages, you begin to have plaque buildup and thickening of the vessel wall. And in the late stage, you get even more plaque buildup due to the dysfunction of the endothelial vascular wall. And you also get hypertrophy. All these changes result in narrowing of the lumen and buildup in vascular pressure, resulting in or aggravating hypertension. These vascular changes can eventually result in end organ damage, which includes stroke, retinopathy, transient ischemic attack, left ventricular hypertrophy, cardiac failure, and renal failure. Some investigations that should be performed in a patient with hypertension include ECG or electrocardiogram to check for cardiac function, urinalysis for renal function, and serology tests such as plasma renin, plasma aldosterone, the thyroid function test, and full blood count to rule out other differentials and to monitor hypertension. Management of hypertension include exercise, reducing salt intake, being on a proper diet, limit alcohol intake, smoking cessation, and use of antihypertensives such as ACE inhibitors.
So it's a risk factor for developing coronary heart disease, myocardial infarction, or cardiovascular disease, right? Blood pressure 140 over 90 under the age of 60, and 150 over 90 under the age of 60. Okay, the risk here again is congestive heart failure, right? Because the heart has to work against the extra resistance, but also the risk of blowing capillary beds, right? If you blow them in the retina of your eye, you have blindness. If you blow them in your brain, you have a stroke, okay? And if you blow them in your heart, you're going to have a myocardial infarction. The risk factors, again, family history, smoking, obesity, sedentary lifestyle, hyperlipidemia, which is just high lipid concentration in the blood, high sodium intake, low potassium intake, high alcohol consumption, stress, and aging. It's been shown that African Americans are at higher risk, and women's risk increases after menopause because of the drop in estrogen levels. So what are some therapeutic nutritional changes that we can use, right? These are basically categorized under the DASH, which is Dietary Approach to Stop Hypertension. It's an acronym. Decrease sodium intake to 2,300 milligrams and gradually to 1,500 milligrams per day for maximum benefit. Low intake of basically salty snacks, canned soup, processed foods. Low fat dairy to promote calcium intake. Include fruits and vegetables that are high in potassium. Cut alcohol, and encourage the client to read labels and understand their food choices, and increase their exercise, promote weight loss, and reduce the intake of alcohol and the use of tobacco. Okay, all of those are going to help you. Okay, so there's a couple of publications talking about the DASH diet. Okay, let's look at what happens when you suffer a heart attack.
Despite ongoing advances in the management of chronic heart failure, patient outcomes for acutely decompensated disease have not improved. Across Canada, patients hospitalized for heart failure continue to suffer frequent complications, and 16.5% die during their initial hospitalization. An examination of the pathophysiology of acute decompensated heart failure identifies promising new avenues for treatment. During heart failure, the heart cannot circulate enough blood at normal cardiac filling pressures to meet the metabolic needs of the brain, kidneys, heart, and other vital organs. The body responds by releasing neurohormones. Certain neurohormones help maintain blood pressure, but over time, they cause heart failure to worsen. One of these neurohormones is renin, released by the kidneys in response to decreased perfusion and increased sympathetic activity. Renin activates the renin-angiotensin-aldosterone system, or RAAS, by cleaving angiotensinogen in the liver to produce angiotensin-1, which is further converted to angiotensin-2 in the lungs. Angiotensin-2 binds to blood vessel walls, causing vasoconstriction. Angiotensin-2 also stimulates release of endothelin from endothelial cells. Angiotensin-2 and endothelin act on vascular smooth muscle, causing constriction of the coronary arteries and systemic arteries and veins. While vasoconstriction helps maintain blood pressure, it can also have maladaptive effects. For example, the weakened heart must pump harder against increased resistance in the systemic arteries, while constriction of the coronary arteries further compromises the myocardium's supply of oxygen. Venous constriction also contributes to displacement of fluid into the lungs and other tissues. Angiotensin-2 stimulates the adrenal glands to release aldosterone. Aldosterone causes the kidneys to reabsorb sodium into the bloodstream, and with it, water. Sodium and water retention cause a state of fluid overload that is exacerbated by venous constriction. Gaseous exchange in the lungs is inhibited by pulmonary edema. Buildup of fluid in and around the lungs increases the physical work of breathing. Patients with acute left-sided heart failure feel short of breath and fatigued. When right-sided heart failure occurs, fluid accumulates in the liver and legs. Apart from the activity of the RAAS, the body tries to maintain blood pressure using other mechanisms, such as releasing epinephrine from the adrenal glands and norepinephrine from sympathetic nerve endings. These catecholamines increase heart rate and contractility, in addition to causing arterial and venous constriction. Over time, chronic volume overload and the activity of angiotensin-2, aldosterone, and endothelin stimulate pathologic cardiac remodeling. The interstitial fibrosis and myocyte apoptosis associated with cardiac remodeling decrease heart wall elasticity, further inhibiting the heart's ability to relax and pump effectively. In summary, the neurohormonal response to heart failure causes vasoconstriction, fluid retention, and increased heart rate and contractility. In turn, these processes initiate a vicious cycle of further myocardial injury and escalating heart failure. Fortunately, additional neurohormonal responses modulate the activity of the RAAS, endothelin, epinephrine, and norepinephrine.
The inability of the heart to maintain blood flow is the definition of heart failure, right? What can contribute to this and what results from this? Excess sodium, fluid retention, and edema, which is just swelling due to accumulation of fluid in the tissues. Risk factors: coronary heart disease, hypertension, diabetes mellitus, and previous myocardial infarctions, arrhythmias, valve disorders, obesity, and metabolic syndrome. Really, when you consider all these, they're kind of the same thing, okay? If you put on extra weight, you create conditions that are going to contribute to diabetes type 2 and to cardiovascular disease, okay? One leads to the other. So it's not like really they end up being separate things. If you have a lifestyle where you take in more calories than you burn and you don't do a lot of exercise, the way that the progression works is that first you gain the weight. Then, because your insulin levels are high all the time, you lose the sensitivity to your own insulin, and then you begin type 2 diabetes. With type 2 diabetes, the sugar levels in your blood get high, more fluid goes into the blood because of the high sugar, and the blood pressure goes up, okay? That also results in sugar in the urine and ketones in the urine and a shift in body pH from a condition called ketoacidosis, and also results in being thirsty all the time, right? Because of the higher blood pressure and because of the excess weight, you're producing more resistance against which the heart has to work, and that can eventually lead to a variety of outcomes. The worst being congestive heart failure, where the heart can't pump the blood out anymore because of the high resistance. The other, because of the high cholesterol and triglycerides in the blood, is going to be the collection of plaque and the generation of atherosclerosis, and the result could be an embolus, right? A floating clot that blocks a capillary bed and puts you at risk for heart attack, stroke, pulmonary embolism, okay? So it's a continuum, really. So again, what do? Cut the sodium, 2,000 milligrams per day or less. Whole milk replaced by low sodium. Content in water should be checked. How much sodium is there in the water? Selected vegetables are allowed. Processed foods limited. Look at the sodium label. Sodium free is less than 5 milligrams. Very low sodium, less than 35, and low sodium is less than 140. Monitor fluid and intake to restrict to around 2 liters a day, and that's again to cut the fluid volume in the blood, right? Keep your blood pressure lower, and then small frequent meals and soft, easy to chew food, okay? Let's look at heart attack.
Cardiac compromise is a blanket term that refers to many kinds of problems with the heart. Just as there are many problems, there are a wide variety of signs and symptoms associated with these heart problems. As an EMT, it is much safer to treat all patients as though they are having a heart problem, rather than diagnose the specific disorder. With that in mind, let's take a closer look at 5 of the most common heart conditions. Coronary artery disease. Coronary artery disease occurs when the coronary arteries are narrowed or blocked, reducing the amount of oxygen delivered to the heart. 2 conditions, atherosclerosis and arteriosclerosis, commonly cause the narrowing or blockage of arteries. Atherosclerosis is a buildup of fatty deposits on the inner walls of arteries. This buildup causes a narrowing of the inner vessel diameter, restricting blood flow. Fats and other particles combine to form plaque. Arteriosclerosis is a stiffening or hardening of the artery wall resulting from calcium deposits. Often called hardening of the arteries, this condition causes the loss of elasticity, changing blood flow and increasing blood pressure. These conditions can facilitate rough surfaces, making them vulnerable to blockages. A large thrombus can cause an occlusion, or it may break loose to become an embolism and form blockages elsewhere. When blockage occurs, tissues may die, and in certain cases, this can be fatal. Acute myocardial infarction. Acute myocardial infarction occurs when a portion of the myocardium, heart muscle, dies as a result of oxygen starvation. The dead area can no longer pump. This can lead to cardiac arrest, shock, pulmonary edema, or congestive heart failure. In some cases, heart attack patients suffer cardiac rupture as the dead tissue area of the heart muscle bursts open. Medications called thrombolytics dissolve clots that block coronary arteries. Other patients receive an angioplasty, a balloon device to open the arteries. Aneurysms. Weak spots that dilate are known as aneurysms. When a weakened artery bursts, rapid internal bleeding occurs and tissues beyond the rupture can be damaged. A rupture of an artery within the brain can result in a severe stroke. If a major artery ruptures, death from shock can occur. Arrhythmia. A malfunction of the heart's electrical system will generally result in an arrhythmia. Electrical disturbances within the heart result in arrhythmias, including bradycardia, abnormally slow, less than 60 beats per minute, tachycardia, greater than 100 beats per minute, or rhythms that are present when there is no pulse, including ventricular fibrillation, ventricular tachycardia, pulseless electrical activity, and asystole. Congestive heart failure, CHF. Congestive heart failure, CHF, is a condition of excessive fluid buildup in the lungs and other organs because of inadequate pumping of the heart or a failure of the lungs to function properly. Congestive heart failure can be caused by diseased heart valves, hypertension, or some form of obstructive pulmonary disease. The symptoms of CHF may include tachycardia, shortness of breath, elevated blood pressure, cyanosis, profuse sweating, cool and clammy skin, pulmonary edema, pedal edema, or the coughing up of frothy white or pink sputum. Late signs include engorged pulsating neck veins or enlarged liver and spleen with abdominal distension.
Myocardial infarction happens when there's inadequate oxygen to the myocardium, which is the muscle layer of the heart that actually does the pumping. And this can occur because of atherosclerosis. There are only two blood vessels that supply the heart muscle itself that come off of the aorta, which is the main blood vessel that carries blood to the rest of the body. And those are the right and left coronary arteries. And if they get blocked, there's really no way to get the blood back to the heart muscle that was supplied by that vessel. Okay, there's no other circulatory path that will do that for you. And within, just a few seconds, you begin to have stress on the tissue and then tissue death, right? And when the myocardium dies, it doesn't grow back. It gets replaced by scar tissue, and scar tissue can't do any pumping, okay? So your heart is weaker from that point on. After an MI, you usually have to reduce myocardial oxygen demands related to metabolic activity because the heart is permanently weaker, okay? The risk factors are the same as for coronary heart disease, right? Liquid diet for the first 24 hours, avoid caffeine, small frequent meals, and then talk about a heart healthy diet and then changes in your lifestyle, okay? One of the things that we need to appreciate is the fact that the heart as a blood pump, okay, has to have a constant supply of blood that it's actually pumping. So the heart actually is the first organ to receive the blood after a heartbeat, right? That blood goes into the aorta, and before it goes to any other organ or tissue, it goes back to the heart itself, okay? And then the heart is able to continue the job of pumping the blood over and over again. And we want to make that as easy on the heart as possible so that you don't put so much strain on the heart that it can't overcome the force that it's working against, or avoid the possibility of the heart enlarging, okay, which is actually an indication that the heart is overly stressed. So this is designed to promote those conditions, okay? If you reduce your body fat and you do exercise and you build muscle instead of accumulating fat, the muscle tissue actually causes more blood vessels to grow in your body. And that's because muscle needs a lot of oxygen and nutrients to do its work. The result of having more blood vessels is that there's less resistance against which the heart has to work. And as a result, the heart rate will go down, your pulse will be low and slow, even after exercise, okay? And that's a hallmark of a trained athlete, is that they tend to maintain low heart rates and low pulse rates even after exertion, because they have all these extra blood vessels supplying these tissues and cutting down on the resistance that the heart has to work against. It's kind of like traffic at 5 o'clock, right? If you've been in Cincinnati trying to get somewhere at 5 o'clock, you know that 75 and 71 are bumper to bumper, usually, okay, at rush hour. Well, if there's an accident, right, or if we cut off 71 or 75, it gets even worse, right? You might not get home for many, many hours. Well, with both highways open, or even if we had a third highway, right, the traffic flow would be much easier because there's more ways to get from one location to another. And the same is true in the cardiovascular system. The more blood vessels you have, the less resistance you have, the less likely the heart is going to have to work hard to pump the blood, and the longer it's going to be able to pump for you. Okay? All right. With that said, we're actually done. Does anybody have any questions before we bump out here a little early today? Everybody got their homework assignment and they got their notes? And next week, right? Let's see, this is 8/20. This is today. Next week is our first exam. Okay.
Okay.
So what I'm going to send you is a practice exam to work on. Okay. And I'll have the grades in for your submitted homework so that you know what's up with that. And then you're going to continue working on your disease project. You can submit that anytime between now and the last day of class. Okay. The practice exam will be questions that are similar to the ones that are going to be on the real exam. I'll include a key, and you take that and you see how you do. And if you have any questions, you ask me. Okay. I'll also get the podcasts of all these lectures up so that you can review and flesh out your notes. And if you have any questions, let me know. My office hours, remember, are 5 to 7 p.m. on Friday. So I'll be here. You can get me by cell or by email. Okay. If you want, we can do a Zoom. Okay. And I'll be happy to help you with any questions you might have. Okay. So any other questions before we bump out? We good?
One before we run away.
Okay.
We got a vacation coming up soon, correct?
Let's see.
Your syllabus don't reflect that.
Oh, okay. Okay. I may have to modify the syllabus and
All right.
and resubmit. Okay. So
Okay.
yeah. So if there's a break, the weeks won't change. The dates will. Okay. So I will check that out. I will check that out, and I'll let you know. Okay.
Okay.
Sound
All
good?
right. Other than
Thank
that,
you.
today's homework, I can turn that in right now, right?
You can if you want to. Yeah. Mm-hmm.
Okay. Great.
Just email it to
All
me.
right.
All right. Well, thank you much. Bye bye.
Have an excellent day.